Okay, in this lecture we will talk about squeeze and play theorem, and this theorem is also known as sandwich theorem, right? So to understand sandwich theorem, you think about these two functions, okay? Let us say I give you a function f of x, okay? And I give you another function which is, let us say, g of x, right? And there is this point a, let us say this is point a on x-axis. At x equal to a, both these graphs are approaching this point, right? I'm not saying that value of f of x at a is this. No. Let us name this point also. Let's say that this value is b. Okay. What I'm saying is that at x equal to a, both graphs are approaching this point, right? Value of f of x may be different. Let's say value of f of x at a is this. So this is f of a. And let's say value of g of x is this at a. So this is g of a, right? So these two functions, if you observe, f of x is always greater than g of x, right? At every place, at every value, f of x is greater than g of x. After this also, this goes up and this goes, let's say, down, right? So f of x is always greater than g of x. At this point also, f of x is greater than g of x, which is f of a is greater than g of a, right? Now, if I take limit x tends to a f of x and limit x tends to a g of x, right? What is the limit x tends to a f of x? What I mean to ask is, when x approaches a, where does f of x approach? It approaches this point, right, which is b. So this limit is equal to b. And tell me about g of x. When x approaches a, where does this graph go? When x approaches a, right, from here or here, the graph g of x approaches this point, right? This is how we look at the limits. So graph of g of x also approaches b. So this value is also b. So both these limits are equal and equal to b, right? So these two limits are equal. Now let me take another scenario. Let us take graph of f of x like this, and let us take graph of g of x like this, right? In this case also, f of x is greater than g of x, and let's name this point as a. Okay, so at a, limit of g of x, what I mean is, if I take limit now, x tends to a f of x and limit x tends to a g of x. Now at when x approaches a, where does graph of f of x approach? At this point, let's say this point is name it b, and let's name it c. So graph of f of x approaches b, and graph of g of x approaches c at x equal to a. So limit at this x tends to a f of x is b, and this is c, right? This time if you see, this limit is also greater than limit of g function, right? So in this scenario, f of x is always greater than g of x, and they do not approach at a single point at any given x, right? Unlike this case, here at a, both the graphs approached this point b, right? The value of the graphs, value of the functions was not b, but they were approaching b, right? This is the difference between these two scenarios. What I mean to say here is that if a function f of x is greater than g of x, and I take limit x tends to a f of x, limit x tends to a g of x, right? Then if I say that this is greater than this limit, right, this would be a false statement. Why? Because we saw in the first case that it was equal here, right? So it cannot be always greater, right? But if I write like this, it is greater than or equal to, so both the cases will be satisfied. Hence, if I say like this, then it will become true, right? Now this is true. So if a function is greater than another function, and if I want to take limit at some particular point of both the functions, then I'll have to apply equal sign here. So greater than or equal to would be the right thing to do. Okay. So now if you take three functions, let us say f of x is greater than h of x is greater than g of x, right? So this was our f of x. Let's say this is our g of x, and let's take that scenario where they were approaching a single point here, right? And if there is a graph which is h of x, that is between f of x and g of x always, right? So this graph of h of x will definitely pass through this point, or will definitely approach this point, right? So at x equal to a, this will definitely approach this point, because h of x is always between f of x and g of x, and f of x and g of x approach same point here. Let's name this point b. Both these graphs approach this point b here, so h of x will also approach this point, right? This is the idea of sandwich theorem, that if there is a function, f of x is greater than that function, g of x is lesser than that function, then if limit x tends to a f of x is equal to limit x tends to a g of x equal to some limit, in this case it is b, then limit x tends to a h of x will definitely be equal to b, right? Because this graph is sandwiched between f of x and g of x, right? So it will satisfy this condition. Okay, so this is sandwich theorem. Okay, and if you want the proof of it, then what you can say here is that f of x is greater than h of x is greater than g of x, right? Now if I take limit, if I apply limit x tends to a, limit x tends to a g of x f of x, and limit x tends to a h of x, right? Now I'll have to apply equality here. Why? Because we discussed in the introduction, this is what we discussed in the introduction, right here. So we will mark it greater than or equal to now, and greater than or equal to now. So if these two are equal, then this definitely will be equal to these. Okay, so this is the sandwich theorem, right? What is the use of sandwich theorem? We can solve various problems which cannot be solved otherwise. For example, if I take a problem, let me take another page here. Okay, so if I take a problem of something like limit n tends to infinity n over n square plus 1 plus n over n square plus 2 plus n over n square plus 3 plus and so on up to n over n square plus 5n, let's say. Okay, so in this problem I cannot separate these terms, right? Because this variable n is tending to infinity. So if I try to separate these terms, what will happen is n, the variable is dependent, right? It varies till infinity. So if I separate these terms, there will be infinite terms. So what will happen is that won't be an appropriate way of solving this question. What I want to do here is I will make use of squeeze and play theorem in this question and solve it. What I mean to say is, if some of the student is thinking that I can separate this into these many questions, right? What will happen is n is tending to infinity, right? So if this limit, let us say n over n square plus 1, if some student is thinking that I'll bring this n here, so it will become 1 over n plus 1 by n, right? So in that case also he will not be able to solve it by separating the terms, right? Because this will become 0, this will become infinity, so 1 by infinity is 0. So some student says 0 plus 0 plus 0 and so on up to 5n terms, but you notice n is tending to infinity, right? If you try to solve like this, you will get 0 into infinity, which is indeterminate, right? So you will get 0 into infinity, which is indeterminate. Hence, you cannot solve it like this. So let's see how we can use squeeze and play theorem to solve questions like this. For to apply squeeze and play theorem, you need a function which is lesser than this given function, right? And you need a function which is greater than this, right? You need a function which is lesser than this, and you need a function which is greater than this. And both these functions should have same limit at n tends to infinity. Then this function will have that limit, right? As per squeeze and play theorem. So, and tell me, out of these denominators, n square plus 1, n square plus 2, n square plus 3, which one is the smallest? N square plus 1 is lesser than n square plus 2, right? So this denominator is the smallest. Hence the biggest term is n over n square plus 1, right? Because this is the smallest denominator, hence this term is the biggest term out of these terms, right? So if I want to make a function bigger than this one, what I can do is n over n square plus 1 plus n over n square plus 1 plus and so on. I can take it n over n square plus 1 how many times? 5n times, right? Why 5n times? Because there are 5n terms here, right? So let me take this function, this term 5n times. Okay, so now this function, this term is definitely greater than this one, right? So this taken 5n times is greater than the given expression like this. Okay, and if I want a smaller function than this, what I can do is this term is the biggest denominator, right? So this term is the smallest term. If I add this term n over n square plus 5n plus n over n square plus 5n plus and so on 5n times, then it will be lesser than the given expression. Why? Because this is the smallest term, right? So this term is lesser than this term, is lesser than this term, is lesser than this term. So if I add this term 5n times, the sum will definitely be lesser than the given expression. So now I have got two functions, one which is bigger than this given function, one which is lesser than the given function. So now if I apply limit n tends to infinity, limit n tends to infinity, and on the given also limit n tends to infinity, then I'll have to convert these inequalities into greater than or equal to, right? Now let's club these terms. Limit n tends to infinity. How many terms are these? These are 5n terms. So I can write 5n into n over n square plus 1, right, is greater than equal to limit n tends to infinity of the given expression, right? Or we can say that this is the required answer and it is greater than equal to this limit n tends to infinity. This term written 5n times, added 5n times, will result into 5n into n by n square plus 5n. Okay, so effectively what I can say here is I can solve this one here. This is 5n square by n square plus 1, limit n tends to infinity greater than or equal to limit n tends to infinity given expression, limit n tends to infinity. This one again is 5n square and it is divided by n square plus 5n. Now you can calculate this limit by two methods. One, you can divide denominator and numerator by n square. So numerator will become 5, denominator will become 1 plus 1 by n square, and 1 by n square will become 0, right? So that this limit is equal to 5, right? If you divide numerator by n square, it will become 5, denominator will become like this, and if you put n equal to infinity, this term will become 0, hence this limit is equal to 5. Okay, similarly in this, if you divide numerator and denominator by n square, the numerator will become 5, denominator will become 1 plus 5 by n. Now if you put n equal to infinity, this term will become 0, so 5 by 1 equal to 5. So both these limits are same and equal to 5, right? So applying sandwich theorem, so using sandwich theorem, we can say limit n tends to infinity of the given expression is nothing but equal to 5. So this is how you can use sandwich theorem to solve questions which cannot be solved otherwise, right? Even if it can be solved otherwise, it might be a difficult solution, right? Sandwich theorem gives a simple solution to this question, right? So let's do one more question, which is also a famous question on sandwich theorem, which says limit, let's write the function first. The function is greatest integer function 1 square into x plus 2 square into x plus 3 square into x plus up to n square into x, right? And this is divided by n cubed, okay, and n tends to infinity. So this is the limit we are supposed to calculate. These two questions are very famous questions on sandwich theorem, and you will find these questions in any of the books or notes that you can have. Now looking at this question will also be solved. This question can be solved by other methods also, but let's use the sandwich theorem in this question. If you have greatest integer function of x, it is always less than or equal to x, and it is greater than x minus 1, right? This is the property of greatest integer function, right? So what I can say here is that greatest integer function 1 square into x is less than 1 square into x, but greater than, less than or equal to 1 square x, but greater than 1 square into x minus 1, right? Similarly, I can say 2 square into x is less than equal to 2 square into x, but greater than 2 square into x minus 1. Similarly, if you go on till n square into x, it will be less than or equal to n square into x, but greater than n square into x minus 1. Now if I add these, so this addition here will give me 1 square x plus 2 square x plus 3 square x and so on up till n square x, right? And it is less than equal to, I can take x common here, 1 square, 2 square up to n square. It is greater than, let me add these ones. How many ones are there? Minus n ones will result into n, and I can take x common, 1 square plus 2 square plus up to n square, right? So if I divide this by n cube, I can divide this by n cube and this by n cube. Now if I take limit n tends to infinity, limit n tends to infinity, limit n tends to infinity, then I'll have to make it equal also, less than equal to, right? This is what we discussed in the introduction. Now this is my required expression which was given in the question. So my required expression is less than equal to this limit and greater than equal to this limit. Now if these two limits are same, then we can apply sandwich theorem and say that required limit is also that answer, right? Whatever answer we get from here and here, if these two answers are same, we can say that this answer is also that same answer. So now let's simplify these expressions. This expression here can be written as n plus 1, 2n plus 1 by 6, right? So this limit can be, let me calculate it here itself, right? Limit n tends to infinity. Now this question becomes x is a constant here because n is the limiting variable. So inside I can write n plus 1, 2n plus 1 by 6 divided by n cube. So this is my question now, right? For this limit. Now if you notice this limit, what is the biggest term in this multiplication? Biggest term will be 2n into n, that is 2n cubed, right? So rest of the terms can be ignored because n is tending to infinity. Otherwise what you can do is you can divide the numerator and denominator by n cube. You will get the same answer. So I leave the calculation part to you. What sorry, what I am going to do here is I'll take 2n cubed, right? Rest of the terms I am ignoring because those will ultimately become 0, right? If I divide by n cube, and in the denominator n cube, so these will get cancelled. So x by 6 into 2 will give me x by 3. So this limit here is x by 3. Now if you calculate this one, look at this one. This portion is same, right? This portion is exactly the same like this, and minus n divided by n cube will ultimately become 0 because this is 1 by n square and n tending to infinity will make it 0. So this will become 0 and this will also become x by 3, right? So both these limits are same and equal to x by 3. So I can say that this required expression, required limit is also x by 3, right? I hope you have understood this question. So this limit here is also x by 3. Okay. So this is the usage of sandwich theorem or squeeze and play theorem. We will do a lot more questions on limits in the upcoming lectures. Thank you.